Hello everyone, I am sure you are all having good time in learning interpretive spectroscopy. So I welcome you all once again to MSB lecture series on interpretive spectroscopy. In my last lecture, I started discussion on charge transfer transitions. So let me continue from where I had stopped. First, let's look into metal to ligand charge transfer. If the metals are in low oxidation state, you should remember that they are electron rich. And the ligand, if the ligands that are coordinated to the metal possesses low lying empty orbitals having pi star aromatic ligands or carbon monoxide or cyanide or olefins, and also sigma star in case of phosphines, sometimes sigma star of hydrogen molecule as well, then a metal to ligand charge transfer MLCT would occur. So MLCT transitions are common for coordination compounds having pi acceptor ligands. You know that I have classified all the ligands that are at our disposal into three categories. Pure sigma donor ligands, they have low energy filled sigma orbitals only. Example, water and ammonia and other related ligands. In that case, what happens? The ligand field stabilization energy or HOMO-LUMO gap is about average. We have another set of ligands, they are called sigma donor and pi donor ligands. For example, halides, they have low energy filled sigma orbitals, and because of three lone pairs, they have low energy filled pi orbitals. When they interact with metals in their high valent state and low electrons, in that case, ligand to metal charge transfer happens. In that case, the CFSE gap decreases considerably compared to what we saw in case of pure sigma donor ligands. That the third class of ligands are sigma donor and pi acceptor ligands. In this case, we have low energy filled sigma orbitals and high energy empty pi orbitals are there. So in this case, what happens? Back bonding would be stabilizing in such a way that HOMO-LUMO gap increases. That's what exactly happens in case of carbon monoxide and phosphines. Upon absorption of light, electrons in the metal orbitals are excited to the ligand pi star orbitals. So metal to ligand charge transfer can also be termed as back bonding. So metal to ligand charge transfer results in intense bands. Example, tris 2,2-bipyridyl ruthenium compound. This is an orange colored complex. It is being studied as the excited state resulting from this charge transfer has a lifetime of microseconds, and the complex is a versatile photochemical redox reagent. And other examples include a phenanthrene ligand of tetracarbonyl tungsten and also 2,2-bipyridyl complex of iron tricarbonyl. Let us come back to now DD transitions. And let us look into how this D and F orbitals will split. For D1 ground state is a 2D state. You can determine that one again using the method I showed you. Two states are there, and then the states are T2G and EG, similar to octahedral splitting, and T2G is lower in energy and EG is higher in energy. This we call it as D term. For a set of F orbitals will be split into three levels in an octahedral field. Two are triply degenerate, one is single. So that means T1G and T2G and A2G. F orbitals will be split into this one, and there both of them are triply degenerate and this is a single one. Now let's consider spectra of D1 and D9 ions. D1 is one electron is there, and D9 one electron less than completely filled electronic configuration. So they have similarities. That's the reason we are considering them together. So in a free gaseous metal ion, as I already mentioned, d orbitals degenerate and no DD transitions are anticipated. In a complex, degeneracy is lost, and in an octahedral field, this d orbitals will be split into T2G, consists of dxy, dyz and dxz, or T2 in case of tetrahedral, and then EG or E consists of dx minus y square and dz square orbitals. Now let's consider a D1 system such as hexachlorotitanate 3 minus or hexa aqua titanium 3 plus D1 system. And then here I have given the absorption maximum value for titanium in +3 state but having different ligands. Okay, and you recall the spectrochemical series and also try to identify the position of these ligands in the spectrochemical series, that would tell you some information. They are in the increasing order of their ligand field strength. Then you can see hexachlorotitanate 3- shows lambda maximum 13,000, whereas fluoro ligand shows 18,900, increase is there, and hexa aqua titanium compound shows 20,300, and hexacyanotitanate 3- shows 22,300. So this is in the increasing order of ligand field strength, okay, and this gap is steadily increasing. And then in case of aqua compound, hexa aqua titanium compound, lambda maximum is 20,300. If you take the spectrum, UV visible spectrum of hexa aqua titanium, this is how it's going to look like here. So the magnitude of delta O depends on the nature of the ligands and affects the energy of electronic transition and hence the frequency of absorption maxima. You should remember that one. This term I have repeated several times. So now let us consider a D9 example such as hexa aqua copper 2+. Splitting of d orbital is very similar to D1 case. In D1 case, one electron is there in T2G level. In D9, one hole is there in EG level. EG level we have dx minus y square and dz square. We have 3 electrons are there. So this is D1 system and this is D9 system. So here one of these electron would be promoted here. That means we have one electron here, whereas here we have one hole here we are considering. So in D1, promotion of one electron from T2G to E, whilst in D9 it is simpler to consider the promotion of hole from EG to T2G. So that means for D9, inverse of D1 energy diagram holds good. That means if you know the transition states in case of D1 system, just if you reverse it, that becomes automatically for D9 system for electronic transition. Now for D9, inverse of D1 energy diagram holds good. So this is for D9 system. So D1 and D9 in tetrahedral also same thing happens. If it is D2, E to T2 is there, and in case of D9 it becomes T2 E1. So this is what exactly happens. By considering this one, what we are doing is we are simplifying for interpretation and elucidation of the structures using the spectral data. Let us look into now different electronic configurations under octahedral as well as tetrahedral, and most of them we are considering are high spin complexes. D1 is a typical one, and D6 we can see here one electron is here, one pair of electrons are there, and D4 will be something like this, and D9 we have one electron here. And then if you consider tetrahedral high spin complexes, it doesn't make much difference. Here D1 one electron, D6 it's very similar, and D4 and D9. So that means all these electronic configurations have some similarities. So D1, D6, D4, D9. D1 and D6 is one electron and one more than half filled. D4 one less than half filled, one less than completely filled. Same thing in case of tetrahedral also. Now is it possible to combine all those things to make the interpretation simple? That's what we do in case of Orgel diagram. In Orgel diagram, what we are considering is we are considering D1, D6, D4, D9 octahedral system as well as D4, D9, D1, D6 tetrahedral system. So all these cases can be combined into a single diagram called Orgel diagram to interpret the data obtained from electronic spectra, which describes the qualitative way of effect of electronic configuration. That means all these electronic configurations of both octahedral and tetrahedral complexes can be combined into a single diagram. We call it as Orgel diagram, which describes the qualitative way of the effect of electronic configuration with one electron, with one more electron than half filled, and one less electron than full shell, and then one less than half filled shell. So that would cover all the electronic configuration I have shown here, D1, D6, D4, D9. A typical Orgel diagram for all this system together is represented here, and D4 and D9 here, octahedral, and D1, D6 tetrahedral is here, again D4, D9 tetrahedral is here, and D1, D6 octahedral is here. For example, D4 system, if one transition is there, we can say it is from EG to T2G, and then D9 also EG to T2G. But if you take D1 and D6, it is T2G to EG, or T2EG. So this is how you can see the representation of all these electronic configurations for both octahedral and tetrahedral complexes in one diagram. This diagram can, without any problem, can explain the electronic spectra provided we have in the complex these electronic configurations. So now let's look into spectra of D2 and D8 ions to see some similarities similar to what we saw in case of D1, D4, D6 and D9 system. So in an octahedral field, what we have is T2G0 and EG is the D2 system, something like this. This is, we can call it that EG0, and then when the electron is promoted, this would change to T2G1, EG1. There are two possibilities for this transition to occur. Electrons may be promoted from dxy, dxz or dyz to dz square or dx minus y square. So less energy is needed to promote an electron to dz square than dx minus y square. So that why probably you can go back to tetragonal elongation and tetragonal compression, you would understand what is the benefit of promoting one electron to dz square or dx minus y square. So now once you promote electron, so we have the electronic configuration of dxy1 and dz square 1, then it is a less energy transition. On the other hand, when you promote electron to dx minus y square, it's more energy transition. So electrons are spread around in all three directions, x, y, z, reducing the electron repulsion. So here electrons are confined to xy plane, because 4 ligands are approaching in the direction of x minus x, y minus y. As a result, if you put more electrons, what happens? The metal to ligand repulsion would destabilize and it will be more energetic. Result, more electron repulsion. In both the cases, electrons are promoted and another high energy state will be formed, thus 4 energy levels will be there. So as a result, we can see 4 energy levels in case of D2 and D8 system. So now consider an example, a specific example of D2 system, hexa-aqua vanadium 3+, and here D2 electronic configuration, ground term is 3f. Already I showed you in my previous lecture, and 4 excited states are possible here, 3p, 1g, 1d and 1s. And the ground state contains 2 electrons with parallel spins. So that means the F state will be split into 3 levels, 2 triplet generate and 1 single, 3 T1G, 3 T2G and then 3 A2G. These transitions are possible. So ligand field strength of water results in transitions occurring close to the crossover point between 3T1P and they are not resolved. But if you just see here why this is not resolved here, I will show here vanadium 3+ ion with 3 different ligands will show 3 distinct peaks. If we have 3 different ligands are there, we can see 3 different peaks here. You can see this is the first one, 3T1G to 3T2G, and then we have 3T1G to 3T1GP, and then we have 3T1G to high energy 3A2G F. So 3 transitions are possible. They are represented here, and 2 have very narrow gap. As a result, they are coming here, and then this is 3T1G to 3T2G here. Okay. So now the way we combine D1, D4, D6, D9, is it possible to combine D2, D8, D3, D7 because of the similarities? In case of nickel 2+, a D8 system has 2 holes in EG. The way we had 1 hole in case of D9 and 1 electron in D1. Here in case of D2 and D8, if you consider D2 we have 2 electrons, whereas in case of D8 system we have 2 holes in EG. Promoting 1 or 2 electrons to EG means transferring the holes from EG to T2G level. So here 3p is not split. 3p is not split because if you recall, all T states p orbitals are triplet generate. We have T1U, we call it as sp3d2 when you consider, or when you go to ligand field theory, the p orbitals are designated as T1U. So they still degenerate. They have the same energy. So they do not split, whereas 3f is split into 3 states and will be inverted here. So 3Ag2 will be ground state term. Similarly, D7 is similar to D2 and D3 is similar to D8 in octahedral environment. If you consider chromium 3+, a D3 system is expected to show 3 peaks. Here what we have shown is for electronic spectrum of hexa-aqua nickel 2+, D8 system, it shows 3 transitions as expected from these explanations. So here A2G is the ground state, A2G to T1GP and A2G to T1GF, and then 3A2G to 3T2GF. So we can see 3 distinct DD transitions here. The same thing is shown here again. So now let's look into these systems to identify the similarities D2, D8, D3, D7, octahedral high spin complexes, D3, D7, D8, D8, D3, D7, D8, D2, tetrahedral high spin complexes. So now again, is it possible to combine the octahedral and tetrahedral complexes having this electronic configuration into a single diagram to explain transitions happening in these type of complexes having D2, D7, D3, D8, octahedral as well as tetrahedral geometries. So here all these cases can be conveniently combined into a single diagram, again called as Orgel diagram, which describes the qualitative way of the effect of electronic configuration with 2 electrons, 2 more electrons than half-filled subshell, and 2 less electrons than a full shell, and 2 less than half-filled shell. So that means basically that covers all, and this is how you can write a typical Orgel diagram. Consists of D2, D7, D3, D8 electronic configuration for both octahedral as well as tetrahedral complexes in this fashion here. Of course, here I have shown 3 transitions of D8 system starting from 3A2G to 3T2G and 3A2G to 3T1GF and then 3A2G to 3T1GP. You can see some difference here. If you see this energy level, it has bent downward, whereas the 3p state is bent upward. So why this is happening? You can see here. So if they have been straight, they would have gone like that. Why they are bending means they are deflecting. The energy one bends further down and high energy level bends further up to minimize their interaction. Why that happens? Here explanation is shown here. There are 2 3T1G states, one each for 3p and 3f state. Both T1G states are curved because they have the same symmetry and they interact with each other. So inter-electron repulsion lowers the energy of the lowest state and increases the energy of the highest state. The effect is much more marked on the left of the diagram because 2 levels are close in energy. That's what we saw. If the lines have been straight, they would have crossed each other, which implies that at crossover, 2 electrons in atom have the same symmetry and same energy. That is forbidden. That is not allowed. That is prohibited. This is impossible, prohibited by non-crossing rule. So state of same symmetry cannot cross each other. The state of same symmetry cannot cross each other. The mixing or inter-electronic repulsion which causes the bending of the lines is expressed by Racah parameters B and C. So B and C can be calculated from linear combination of exchange integral and Coulomb integrals, but they are obtained empirically from the spectra of the free ions. So that means basically to what extent, that means when you predict from theoretical values, they are different from the observed or experimental values. So in order to make the correction so that the experimental values would be same as theoretical values, you have to incorporate Racah parameters. So these Racah parameters B and C can be calculated from linear combination of exchange integrals and Coulomb integrals. And how to obtain them? They are obtained empirically from the spectra of the free ions. So now let's look into the chromium 3 state, how here splitting happens having 4f and 4p states here. You can see here F state is lower in energy and P state is increasing energy because of mixing, whereas these 2 states are not affected. So that means basically when we look into observed and measured data, there is no change in this transition value, whereas you can see decrease in the value of this one, whereas increase to this extent here. So we have to account for this in both the cases, decrease as well as increasing. For transition between the same multiplicity state, B is enough to explain the position of the bands. For different multiplicity, we need both the value of B and C. In case of D3, for V2 plus ion, vanadium 2 plus ion, separation between 4F and 2G is 4B plus 3C. So for B is approximately 700 to 1000 centimeter minus and C is 4 times that of B. So due to the mixing of P and F terms, energy of 4T1GP is increased here by an amount X, this you can call it as X, and that of T1GF is decreased by an amount Y, this is Y. and this is X. So now let us come to understanding this anomaly here. We use the term nephelauxetic effect. So now let us consider again chromium 3 plus ion D3, and B and C are known. B value is 918 centimeter minus and C is 4133 centimeter minus. Now the observed value is 14,900, and then this is 22,700, and nu 3 is 34,400. So predicted one is there is no change, and then here it is predicted one is high 26,800, and then this one is low. We know that this is going up, so it is high, and then this is going low, so this is low. So compared to observed values. So B relates to a free ion. The apparent value of B prime in a complex is always less than that of a free ion value, because electrons on the metal can be delocalized into MOs covering both metal and the ligands. So use of B prime improves the agreement. This localization is called nephelauxetic effect, and nephelauxetic effect ratio is given by beta equals B prime over B. Beta decreases as delocalization increases, but always less than 1. B prime equals 0.7 to 0.9 B. If all the transitions are there, then 15 B prime equals mu 3 plus mu 2 minus 3 nu 1, or 15 B prime equals 15 plus 2 plus 18 minus 30. This is the value you can take. And then of course Raka parameters for B, Raka B for transition metals in plus 2 state and plus 3 state is available. One can take directly from literature. And then when you apply here, as I mentioned, this increases by X and this decreases by term Y, and then we add these values and do the correction. Of course no change here, this is coming very close now, 18 dq minus X, and here 12 dq plus 15 B prime plus X, it would come around something like that. So now after correlation it comes very close to the observed value, and magnitude is about 34,400 plus or minus 400 is allowed, and similarly here 22,700 and 22,400 plus or minus 300 is allowed, and here it is very accurate because there is no change in the electronic levels. So this is how we can use Raka parameters to do corrections for the theoretical values so that that tallies with the observed value. So let me stop here and continue in my next lecture about spectra of D5 ions, high spin D5 ions. Okay, so thank you so much.